Welcome to a lesson with Dr. Powell. In this video, let's take a look at an example of a related rates problem. Suppose that we want the surface area of this cylinder or can to remain constant. While it's remaining constant at 20, the radius is actually changing. It's growing at a particular instant at the rate of 1 inch per second. I want to know how fast the height will be growing at this particular moment in time. Now we also need to specify a little bit. At this particular moment in time, let's suppose that the radius is 2. All right, so the radius is 2. Might be getting kind of flat there at that moment. In particular, let's think about that if this actually makes sense, because that means the area of the base would be pi r squared. So 4 pi is like 12. Actually, that doesn't quite make sense, because if you think about it, 4 times, that's like 12 and 12 on the top and bottom. That's already over 20. So r is equaling 2 is not a good setup for this particular problem. Let's make it smaller. I'm going to keep that in the video just so you can kind of see that things need to make sense here. Okay, I mean, if you thought about it, that would be too much surface area. Make sure things make sense in your problems. All right, let's suppose when r is a half. Maybe that would be better, because that would be then, yeah, that would work well. Okay, so when r is equal to a half, and you can double check it with the surface area. Surface area of the top and bottom is less than 20, definitely. So we can, because it's pi r squared, so pi times a half squared, so pi fourths. Oh yeah, all right. So that's less than 1. So we're pretty good there. All right, so in this situation, let's figure out what dH dt is. We need to have an equation that relates r and h together, so we can have an equation that relates dr dt and dH dt together. So a function equivalence equation relates functions of things where r is a function of time and h is a function of time. All right, so to do so, let's think. Well, we have something with surface area, right? Might be a good place to start. And the surface area is remaining 20 as a constant, meaning if we have an equation for the area of the top, or if we have an expression that gives us the area of the top and the area of the bottom, and then the side lateral area, add them together, it should be equal to a constant function, 20 in this case. That'll be nice for taking derivatives. All right, so we can think the area of the top and the bottom is the same. So we can think 2 times that area, which is simply pi r squared, keeping r as a variable, that is, in our function equivalence equation here. 2 pi r, and then we want to add, right, because we're still finding area, plus, yeah, what is the area of, so this is the area of the base, okay, just so you know that, and we're doubling it because we want to get top and bottom, okay. But add, we're going to take this, and maybe we should take some scissors to it for a minute. If you cut it, stretch it out and roll it out, the height is h, and what's rolled out here is actually going to be 2 pi r. So why is it 2 pi r? Because that's the circumference of a circle, and that's going to be the length of this when we cut this right here, and then unwind it, pull it out that way, stretch it out, you get a nice sheet here. Circumference of circle, 2 pi r, and an h. Multiply them together, you get 2 pi r h, and that's going to be equal to 20. We want that to be equal to a constant 20. There's our function equivalence equation that relates the function r and the function h together. Notice I'm calling the variables functions because I want to emphasize that we can take derivatives of them, right? And that they're chunks. and they're functions of t. So that's why I'm saying a function equivalence equation. All right, and this side, of course, notice you have a 2 pi, 2 pi. You can factor that or divide both sides by 2 pi, and you would be left with 10 over pi on this side is equal to r squared plus rh. Kind of a nice equation there, relates r and h together. Now, so that's our function equivalence equation. Now to get our derivative equivalence equation. This is a function, that's a function, and they're equal. This constant function is equal to this function. Like you take this function, you square it, you add those two functions multiply together, you actually will get a constant function out of it. So you take the derivative of this combination of functions, which is a function itself, and this guy, you would get on both sides, you get derivative of 0, right? Derivative of this part is 0. And let's see but we can write down the derivative of this using our derivative rules here. So we can use chain rule and power rule here. Our derivative of r squared is 2r dr dt plus, and then here we can use a product rule. Okay, we get dr dt times h plus r dh dt, thinking of r and h as functions. Great, because now we are relating dr dt and dh dt together. In fact, we know that dr dt at this moment is going to be 1. So 1. And dr dt is going to be, okay, plus 1. And we know what r is at this moment. It's a half. We have 2 times a half. That's just 1. Okay, so 2 times a half is 1. I'll just write that out. Okay, but plus 1 times height. Oh, we gotta know what the height is at this moment in time. Well, I told you what the radius was at this moment. How would we get the height? Well, look at this equation right here. We can actually figure out what h is from this equation at this particular moment in time, because now we're just plugging in values. But how do you get the moment? But notice r and h are related to each other in such a nice way, with surface area being 20, that we could actually figure out what h is when we know what r is. So here we have 2 pi times 1 squared plus 2 pi times, and I guess we could have gone to this equation down there. That would be easier. Again, I'll leave that in the video just so you can see. Sometimes things can be done more simply. So we can use this because really this equation's equivalent to that one. All right, so at this moment in time, r is a half. R squared is a fourth. Plus r, which is a half, times h is equal to 10 over pi. So we could figure out what h is at this moment. We could subtract both sides by a fourth, so 10 pi minus a fourth is equal to a half times h. Then multiplying both sides by 2, you just get h on this side, and then you get 20 pi minus a half. I distributed the 2 through in the multiplication. It'll be 20 over pi, and 2 quarters is a half. All right, so just a half shy of 20 over pi is h at this moment. All right, so we can have 20 over pi minus a half, and then plus this moment we know that r is a half. Okay, so we put a half times dh dt, which is the unknown. Now the derivative of this side was a constant 0, so all right. So now, and and we've already plugged in values for all of these things that we knew, and we just have to solve for dh dt now. So this part is just a 1, so that's a 1. That's 20 pi minus a half. But you have 1 and then minus a half, that'd be a positive a half, right? So this is really 20 pi plus a half. If you put all this together, this is equal to 1, right? Because I'm adding that's negative a half to make, and distributing here, you can just ignore those parentheses there because 1 times anything is just itself. So you have, so this is equal to a positive 1/2. You take that with that negative 1/2, you get positive a half. So really this side is just 20 over pi plus a half plus a half dh dt. And then you have to think, okay, just move this part 20 over pi plus a half on the other side. So you get negative 20 over pi minus a half, and that's going to be equal to 1/2 dh dt. Multiply both sides by 2, and you get dh dt is equal to negative 40 over pi minus 1, because we multiply both sides by 2. That's a 40. Okay, so notice this is going to be a negative number. Does that make sense? So the height is decreasing as the radius is increasing. It should, because if the base and the top are getting bigger, then the side lateral, the lateral area on the sides has to be getting smaller so you can maintain a surface area of 20. What are the units for this dh dt? This is inches squared for area, so this better be inches per second. So inches per second, and that's dh dt. All right, and that'll conclude that example. Thanks for watching.